Okay, so yes, I'll get those graded and I'll post the scores up as soon as possible. One rule is I don't let students keep their graded quizzes. So if you'd like to take a look at the quiz and see what you got wrong or whatever, you can do so during office hours. Just send me an email. Let me know that you'd like to take a look at your quiz, and I'll bring it and make sure you can view it. And because I have the practice quizzes already posted online, and I feel like the practice quiz is fairly representative of the actual quiz, I don't feel like I'm depriving you of a study resource by holding on to the quiz themselves. And so you're always allowed to email me and ask to view your actual quiz and see what you might have gotten right or wrong. Okay? So I'll have the grades posted as soon as possible, and then and if you want to take a look at it, you can do so during office hours next week. Just send me an email. Okay, we will continue on in our study of statistics, and we are continuing on in chapters 2 and 3. We are still in the section on descriptive statistics. Okay, so today we'll cover chapters 2 and 3. Okay, and this is just more descriptive statistics. So last week we kind of introduced ourselves to the topic of statistics, and what did I say is kind of the thing that statistics offers us as a subject of study? Why do we study statistics in particular? Okay, so we said statistics helps us understand the world around us, but in particular, what does statistics allow us to do? Yeah. Yeah, so we can make conclusions about a large group, like the population, based on findings from a sample. Okay. And I said to accomplish that, first we have to be able to describe the sample, okay, describe the data that we see in the sample. And then once we can describe that, then we will learn later on rules about probability, and that will allow us to generalize and make conclusions about the large population based on the sample. So we're still in this section of being able to describe a sample, okay? Last week, we learned how to describe categorical data. We learned how to summarize that with summary tables and two-way tables, percentages or relative frequencies as they might say. So last week we learned about how to describe data if it's categorical. And this week we will learn how to describe data when it's numeric. Okay, so so I'll say last week we said, statistics allows us to make conclusions about the population based on limited data, or specifically a sample of data. Okay, and so we will first learn how to describe or summarize our data. Okay, and that's descriptive statistics. So last week we learned categorical data with and the tables. What do we call those tables? Frequency tables. Frequency tables. If we get two categorical variables, then we have two-way tables. And how do we display categorical data? That's, I can see you mouthing it. Bar charts. Okay. All right, and so today we will learn how to describe and display numeric data. Okay, so as far as displays go, we will have the dot plot, the histogram, and the box plot. Okay, and to describe with numeric summaries. And there will be kind of several that we'll talk about. We'll have the mean, the median, the standard deviation, and the IQR. Okay, so this is kind of what we will cover today. And again, this is all just to kind of keep sight of the big picture. This is all just under the heading of descriptive statistics. Okay, so if I may continue. All right, so we'll start with just some of these displays here, okay? We'll start with a dot plot. Okay, so you could imagine having gathered a bunch of data, okay? So let me, I'm gonna just pause here. Okay, so here is some data that shows how many goals a college athlete scored. Okay, some soccer players. Okay, during the season. Okay, so some of the athletes scored 9 goals. You know, some scored as many as 35. Okay, and you know, a bunch scored 11. You know, a bunch scored 13. And so these are all listed out. Okay, and we're going to create a dot plot. Okay. And what a dot plot does is it displays one dot for every data point. Okay, on the number line. So if I may, I'm going to just copy this display right here, and so what we have here is a dot plot, and we can see, along the bottom we have a number line, and it's labeled goals because our data is the number of goals scored by a college soccer athlete in this season. All right, and so we see, this person who scored 9 goals is represented by this dot right here at 9, okay? Nobody scored 10 goals, so there's no dot at the 10. And then we see there's 1, 2, 3, 4 people who scored 11 goals, and we see 1, 2, 3, 4 people whose 4 dots show up at 11, okay? And then we have 1 dot at 12 because there's 1 person there. We have 5 people who scored 13, 3 people who scored 14, 2 people who scored 15, and so on, okay? And so every number that appears here is represented by a dot in our dot plot, okay? So every value in our data set or in our sample is represented with a dot. Okay. And from this, we get a sense of kind of what the typical amount of goals scored is. What seems to be like a typical value for goals scored? Yeah, something around 15-ish, okay? 15, give or take 1 or 2 goals, something like that. That seems to be a pretty standard amount, maybe 14, okay? So 14, give or take 1 or 2 goals, and that seems to cover, kind of the bulk of people in here, okay? And so if somebody says I scored 20 goals there, you'd say, oh, that's quite a few. That's on the upper end, okay? And then this also points out, how remarkable someone who scored 35 goals is, okay? So, because when we just look at the numbers all in a line here, we don't really get a good sense of what the values are like. But when we kind of line them up, show them in the dot plot, we get the sense that, quote unquote typical number of goals is about, maybe 14 or 15. Okay, give or take 1 or 2. Okay, and then the dot plot also shows us how 35 is vastly different from everyone else. Okay. Is that good with everybody? Okay. Now we can take this and I can create another plot called a histogram. Okay. And basically, to turn a dot plot into a histogram, it's quite easy. All you have to do is you just kind of, instead of representing everything with a dot, you kind of just turn everything into a bar, okay? And so here I will have a bar, and basically I would just I probably need to make these bars just a tiny bit and then we would just kind of like shade in all of these bars here. And this would be a histogram, okay? So if we, instead of dots, we use bars. Okay, and you know, in this one, I didn't really shade them in, but let me see. I can't see what I'm doing here. But, you know, we wouldn't actually have the dots. This looks more like what a histogram should look like. Something like this, okay? This would be the histogram. So no dots showing up there, but basically I've just gone from dots into bars, and we have a histogram, and it shows the exact same data here, okay? So this would be called a histogram. Now, one advantage of the histogram, rather than showing over the dot plot, is that we can create bins. Okay, so we can create a frequency table. Essentially, what's a frequency table? Okay, and we'll say bins for goals. So a traditional frequency table would say, you know, 9 shows up once. So let me on the previous page, you know, if we were to make a frequency table over here, it would look something something like this. We would have goals, and we'd say 9 shows up once, the number 11 shows up 4 times, the number 12 shows up once, the number 13 shows up 5 times, etc., etc. Okay, so that would be a frequency table for the goals that show up in our data here. Is that okay with everybody? Okay, and so with a histogram, we would create bins for the goals. So rather than just saying 9, 10, and so on and so forth, we can say 9 through 11, okay? And then we would go 12, so 9, 10, 11, 12, basically 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and then 24, 25, 26, 27, 28, 29, so on and so forth, okay? And so our bins for goals, we would have the frequency, and we would count how many numbers show up 9 through 11, and we would have a frequency of 5. How many show up between 12 and 14? 12, 13, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many show up between 15 and 17? 6, and 18 through 20, 6, 21 through 23, 1, and then we've got a bunch of zeros, and then finally when we get up to something, you know, 30, 31, 32, 33, 34, 35, we would have 1. Okay. And so here we have, we've created bins for our goals, and then we can create the corresponding histogram based on that, and it looks like this. Okay, and so we can see, yes, 9 through 11, and it doesn't show 11 here, it just shows 12, but the kind of the style that is chosen is that basically you just show the number for the left bound, okay? So basically 9, 12, 15, 18, and then it's assumed that the other bound for this bar between 9 and 12 means this bar represents everything between 9 up to 11 or 11.9, and then this bar represents everything from 12, 13, 14.9. And so we can see here we have 5, 9, 6, 6, 1, and we got 0, 0, 0, and then 1. Okay, and so this is the construction of a histogram. And there's a question, which is better, this histogram or this histogram, okay? The underlying data is the same for both of these, but these two histograms look quite different, okay? The data is the same for both histograms. Okay, but they look quite different, right? So, because we use this exact same data, and effectively this fed into here, which fed into this this display right over here, right? So which is better? That's kind of a matter of opinion, I guess, and it would be tough to say. Okay, actually, and so the histograms will vary depending on how wide or how thin you've decided to make your bins. Okay, the book actually shows the this same histogram, but they've kind of just stretched it out right here. This is if we have bins of width 1, this histogram, you can see that, I don't know, can you guys see that this histogram is exactly the same as this one if I just stretch it out? Let's see. Like if I compress this, it looks the same, right? So how it is to be done things will look the same, but the underlying data is all the same in all of these cases. So histograms can look different, but they still capture the essence of the data here, which is what is the typical amount of goals? We would probably say something about 15. And from the histogram, we can still see that getting 35 goals or something out here, there was one person who scored way higher than everyone else. Okay, so we still get a sense of what is typical versus what's unusual. Okay. Still provide a sense of typical versus unusual values. Okay. Now, what we can do is we can also take histograms and we can kind of summarize the shape of a histogram with maybe just like a single curve. Okay, so here's a dot plot and here's a histogram showing the same data. Okay, it was the percentage of people who passed the bar from their law school. Okay, so we looked at a bunch of different law schools, and some of them have everyone passing the bar, and some have very few people passing the bar. But basically, this is the same data, and we get the overall sense that they're the same. And so we can kind of summarize this shape, the shape that we see, with something maybe maybe something that looks like this, okay? So here I'm just kind of summarizing the shape with this curve, okay? Okay, and so when you see this curve or this representation, what does this signify? This signifies the kind of the underlying data. And what does this mean? This means that, you know, the typical pass rate for these schools was approximately what? Hmm? Yeah, around 80 to 90%. Okay, I would agree with that. And then let me just get rid of this here. So it seems like, you know, typical is around 80 or 90. Do we have so yeah, maybe like 85 or something around here. This seems to be around the quote typical. Something around here. And then, and what we have is that, you know, the highest you can get was 100%, okay? But there were some places that scored way lower than that, right? Or had a much lower passing percentage. Okay, so this shape is called left skewed. And it can also be described as unimodal. Okay, left skew is the idea that you have this pointy side, this tail to the left. Okay, and unimodal means that there's just one peak. Okay, and so we would say this is left skewed, unimodal. All right, and so to be left skewed means wherever typical is, you can have some values that are way below typical, okay? So be, you know, think of what is typical, okay? And then if it's left skewed, you can have values that are far below typical. Far below, or what we mean by far below is to the left, right? Okay, because you always draw numbers, small numbers on the left and large numbers on the right, okay? So if it's left skewed, you can have values that are far below to the left, okay? But you will not have values far above. Or to the right. Okay, so you can have values that are way below, but you're not going to have values way above. Because here it seems like the typical passing rate for, you know, for the law school graduates is about, you know, around 85% of students pass the bar exam after graduating law school, okay? But there are some law schools where the passing rate looks to be around 20%. Other law schools where the passing rate of their graduates is maybe 50% or something like that. Okay, that's far below what typical is. So if typical is around 85%, you know, to have a pass rate of 20%, that means that school is 65 percentage points below the typical pass rate. Okay. Can anyone be 65 percentage points above the typical pass rate? No, because the highest passing rate possible is 100%. Okay, if everyone who graduates your school passes the bar exam, that's the best you can do, and that would be 100% pass rate. And that would be a good thing, but yeah, that's the highest you can get. So this chart is left skewed. Does that make sense? All right. Well, what do you think it would mean to be right skewed? And can you think of anything that might be right skewed in its distribution? So right skewed would have a shape that looks like this. Okay, and that makes sense, I believe. Okay, you'd have a tail pointing to the right. So this would be right skewed. And can you guys think of something that would be right skewed? Yeah. Okay, yeah, then the soccer players, that one would have been a right skewed shape because we had someone who scored far above average and no one scored that much below. I would say income. Income is something that's always been right skewed, okay? Let's say today in the United States, maybe typical family income or household income is, I don't know, in the vicinity of $60-something thousand, okay? So typical. So we can say typical is between, I don't know, $50,000 to $100,000, okay? So maybe we'll just call it an even 60,000, okay? So that could be a typical income, all right? Are there people making $1 million a year? Okay, so some make 1 million per year, okay? How much above typical is 1 million? Okay, that would be, that is, 940,000 above average, okay? What does it mean to be 940,000 below average? Okay. 1,000 below average or below, 60,000, our typical value would be negative, let's just do this. Okay, so 60 minus 940, negative $880,000, okay? Can anyone have an annual wage of negative 880,000? No. Huh? Well, you can be in debt, but that's not going to be your wage, okay? As far as employment and how much somebody's going to pay you, okay? No one's going to pay you. You cannot be paid a negative amount of money, okay? You might have made some bad investments, but that's just separate from, I guess, a wage or something like that, okay? So, not possible to be paid negative amounts of money. Okay. So income would be an example of something that's right skewed, where you have kind of the bulk of people, probably between 20 to 100 something thousand dollars. That would probably cover 90% of people, 95% of people, and then you just have a small fraction making kind of extreme amounts. All right, and that's just how that goes with income, and other types of things can be right skewed. So this would be right skewed. Okay, is that all right? And this, something like this, would be, well, it's supposed to be symmetric. Okay. Okay, and what does it mean to be symmetric? Yeah, you can have extremes on both sides, right? Extreme values exist on both sides. Okay, here, most are in the middle. Okay, so something like height, human height, is symmetric. Okay, most people are kind of in the middle in terms of human height. So, the vast, a lot of people are between 5 feet and 6 feet tall, or maybe just a shade under 5 and, a few inches. So probably if I set some range like 4'10" to 6'4", that probably covers 90-something% of people, okay? And then, but you have some people who are way taller, okay? And they probably, we see a lot of them because they become professional athletes, okay, a lot of these really tall people. But then you also have people on the other side, extremely short, okay? And so you're gonna have extremes on both sides for human height, okay? And there's other things where you kind of have the bulk in the middle, and then you have some extreme values, both that are way higher and extreme values that are also way lower. Okay, and so that's what it means to be symmetric. Okay, all of the examples that we've shown so far have been unimodal, meaning one peak. So whether it's left skewed or right skewed, unimodal just means one peak. Okay, so these have all been. This looks almost like a face here. But then you can have bimodal. Bimodal would mean we have two peaks, okay? Something like this, okay? And so that could be, I'm trying to think what could be bimodal in distribution, but if you have kind of like a mixture of two different populations and you merge them together, you might see something bimodal. So yes. Work productivity
during lunchtime.
Oh, okay, so that would be you're looking at the relationship between productivity and time. And here we're just looking at one numeric distribution here. Okay, so just one numeric distribution. We're not looking at a relationship between one variable and another. Okay, so we might see something like this if if we looked at hair length. Okay, we might see something that is bimodal, okay? And it probably, so if we looked at, the general population and we measured, hair length, we would have a lot of people who are either bald or very, very short hair, okay? So you'd have a lot of people, and then, a lot of people keep their hair short, okay? And then there's also a lot of people with long hair, and there's, you'd probably see something, and there might be kind of this in between length of hair that's so a lot of people have hair either a little bit past their shoulders or things like that, but then there might be just this in between length of hair that is a little bit less common than kind of like crew cut length, which is just a couple a short length or a few inches long, and then you'll have this kind of this in between length that is less common, and then probably, I don't know, at least down to the bob length or something and longer. So So you might have something that's bimodal, where there's kind of a one dip where there's a certain length that is less common. I'm trying to think other things where you're going to have a dip showing that this particular value was less common. But it's keep in mind we're just looking at one numeric variable, okay? And then sometimes you'll have even more than 2 peaks, okay? And we kind of just say these are like multimodal distributions, okay? Okay. All right. Is that okay right there? Okay. So this was, you know, we've shown you dot plots and histograms to kind of display numeric data. We're going to move on to chapter 3 here and just talk about how we can summarize our numeric data. And after we learn some of our summary things, we've got one more display called the box plot. But it doesn't make sense to talk about the box plot until we talk about certain numeric summaries first, okay? Summaries, or we might call these summary statistics. Okay, or just plain old statistics for numeric data. Okay. And all a summary statistic is we are just taking a bunch of data, okay? So generally our data is from some kind of sample, and we're just trying to boil down our data to a few numbers that give us a sense of the underlying data, okay? So, you know, so we have, you know, a sample of data, okay, which could consist of, you know, hundreds of observations. Okay. And a summary statistic just boils all of those observations down to just a few numbers, okay? Just a few values that give us an idea of those underlying observations. Okay, and so, you know, we'll take a look at some of them, like the mean and the median, the standard deviation, and the IQR, okay? Because they boil down and they highlight just certain aspects of that sample of data, okay? But, you know, this is a concept that you guys are already very familiar with, okay? So, you know, if you're here at school, you know, you're familiar with something called the GPA, okay? GPA, or your grade point average, is an example of a summary statistic. Okay, what it's supposed to do, okay, the GPA tries to summarize your entire academic performance and career into a single number. Okay, and in fact, if you think about it, the final grade that you get in a course, that is also a summary statistic, and it's supposed to summarize how you did in 12 weeks of school, or 16-week course, or whatever. It's just a single value that's supposed to summarize your performance, and the GPA is a summary of all of those summaries. Okay, and so that if somebody says I have a 4.0 GPA, it tells you a lot. It doesn't tell you a lot, but it gives you a good sense of what kind of student this person is. Compare that to someone who has a 2.0 GPA. You get a sense of what kind of grades the other student has. Okay, and of course, it's hard to something as complicated as school performance over many different courses and different subjects and different majors and all of that. It's hard to just boil it down to a single number. But in terms of trying to make quick comparisons from one student to another, it's a useful tool to have. Okay, but you're right. If we were to just compare two students and one has a 3.6 and another has a 3.7 or something like that, is there a real difference between these students? Maybe, maybe not. We'd probably want to look further into what kind of classes these students took, and so we might ask for their transcript or something like that, and see what classes each student took, and all of this. But basically, we're just looking at summary information, and if you're like an admissions department deciding whether or not to let a student into your university, you're trying to just look at this summary of who a student is and make a decision. Okay, and so it is useful to have these summary values, but it also doesn't tell the whole picture. Okay, but at the same time, you still get a good sense of the underlying values there. Okay, and so that's basically the point of a summary statistic, is that it boils it down to just a few values that give us an idea of those observations, and summary statistics are especially useful when comparing kind of one set of data to another set of data. Okay, so summary statistics are especially useful one set of data to another set. Okay, and so so GPA is a summary statistic that was made for an academic setting. Okay, we have summary statistics made for to kind of get a gauge on economic prosperity for a country. So we have things like GDP, or people will talk about the unemployment rate to get an idea of how the economy is doing today versus a few years ago. And they might say the unemployment rate has gone down, or the unemployment has gone up, and this is supposed to be a sign, a way to summarize overall the health of the economy is doing well or doing poorly. Okay, the overall economy it's a complicated thing, but we can just look at a couple numbers and get an idea. Or if you're into sports, there's all sorts of summary statistics for each player. Okay, so you can look at one basketball player and another basketball player, and you can compare points per game or rebounds per game. Or you can look at one baseball player and another baseball player, and there's a summary statistic like batting average or on-base percentage, or just these different values that, without even watching this player play baseball, you can just compare one number to another and get a sense of the player's performance, okay, when just trying to make quick comparisons from one to another. And so there's all sorts of summary statistics that are kind of tailor-made for different situations. And but here we have some kind of generic summary statistics that will work in any for any numeric variable. Okay, so some summary statistics. That will work for any numeric data set. Okay, and we have the mean and the median, and these are they summarize central tendency, or another way is you know, what value is, quote, typical. And then we have standard deviation, and IQR, which stands for interquartile range. And this summarizes, these summarize dispersion or spread. Okay. I'm going to go ahead and we'll pause here, and we'll take maybe a 10-minute break, and we'll come back and delve into each of these.